through projects. In this video, we are going to explain about the project, which is a novel intrusion detection system for Internet of Healthcare Things based on deep subclasses dispersion information. Introduction of the project. The Internet of Healthcare Things, which is IOHT, offers significant benefits to the medical sector, but it is accompanied by concerns and risks, particularly regarding the handling of sensitive medical information and security constraints. Addressing these challenges requires deploying effective security measures tailored to the unique constraints of IOHT systems. This project proposes a novel approach to enhance security in IOHT through the development of a subclass intrusion detection system. The objective is to overcome concerns, mitigate risks, and meet IOHT constraints by improving the discriminative power and classification performance of intrusion detection systems. The proposed approach, termed Deep Subclass Dispersion One Class Support Vector Machine, which is Deep SDO-SVM, utilizes a variation of standard OSVM that considers subclasses within the normal class to minimize data dispersion. Additionally, a deep clustering model, the dynamic autoencoder, is employed for subclass generation to enhance classification performance. Evaluation of the proposed deep SDO-SVM approach on the TON IoT real-world dataset demonstrates superior performance compared to the other state-of-the-art one-class classifiers for network intrusion detection. By considering subclasses and leveraging deep clustering techniques, the approach achieves enhanced discriminative power and classification accuracy. Coming to the objective of the project, the aim is to develop a deep learning based subclasses one class anomaly detection system tailored for the Internet of Healthcare Things, which is IOHT, with the goal of enhancing security measures by accurately identifying abnormal activities while minimizing false positives. The objective is to utilize TON IoT dataset on the basis for training, testing, and evaluating the proposed anomaly detection system, ensuring relevance and realism in the evaluation process. The goal is to build and compare the proposed anomaly detection algorithm with the existing techniques such as Gaussian mixture model, support vector data description, which is SVDD, one-class support vector machine, which is OSVM, multi-class one-class support vector machine, which is MOSVM, one-class neural network, and subclass dispersion, one-class support vector machine to evaluate its effectiveness and superiority. The objective is to predict multiple classes of anomalies, including benign, scanning cross-site scripting, distributed denial of service, which is DDoS, and injection attacks, among others, to ensure comprehensive anomaly detection coverage. The aim is to assess the performance of the proposed anomaly detection system using metrics such as accuracy, precision, recall, and FN score, providing a comprehensive evaluation of its effectiveness in detecting and classifying anomalies in IOHT environments. To implement this project, we need software and hardware requirements. In hardware requirements, we need operating system of Windows, processor of i5 and above, RAM of 8 GB and above, and hard disk of 25 GB and above. Coming to software requirements, we need application of Anaconda, primary language of Python, front-end framework of Flask, back-end framework of Jupyter Notebook, database of SQLite 3, front-end technologies of HTML, CSS, JavaScript, and Bootstrap 4. To implement this project, we have designed various steps in the flow of work. Coming to the first step, which is importing the packages. In this step, we import essential Python libraries like Pandas, NumPy, Seaborn, and Matplotlib, and sklearn. We imported Pandas for data manipulation, NumPy for numerical operations, Seaborn and Matplotlib for visualization, sklearn for various machine learning tasks. The next step is exploring the dataset. Here we load and examine the TON IoT dataset. We check its structure, content, and the data types to understand the information it contains and how it is organized. Data processing. This step involves preparing the dataset for analysis. Here we create Pandas data frame to handle the data efficiently, and then we remove unnecessary columns that won't contribute to our analysis. Visualizing using Seaborn and Matplotlib. We use Seaborn and Matplotlib libraries to visualize various aspects of the dataset. This includes creating plots like histograms, scatter plots, and heat maps to explore relationship between variables and identify patterns and the trends. The next step is appending selected features to X and target column to Y. Here we separate the dataset into features as X and the target variable as Y. Features are the input variables used to make predictions, while the target variable is that what we want to predict. Splitting the data into train and test. Here we divide the data into two subsets, which is Training set and testing set. The training set is used to train machine learning models, while the testing set is used to evaluate its performance. The next step is building the model. In this step, we initiate and define the models. The next step is training the model. Here we train the selected model using training data. The model learns patterns and relationships within the data to make predictions. The next step is Flask framework with SQLite for sign up and sign in. Here we implement a web application using Flask framework. We integrate SQLite database for user authentication, allowing users to sign up and sign in securely. The next step is user gives input as feature values. Users provide by entering feature values relevant to the anomaly detection task. These feature values represent various attributes or the characteristics of the data being analyzed. The next step is the given input is pre-processed for prediction. Here we pre-process the user provided feature values to ensure that they are in the correct format and compatible with the model's input requirements. This involves tasks like scaling, normalizing, and encoding categorical variables. Trained model is used for prediction. Here we use the trained model to make predictions on the pre-processed input data. The model predicts whether the input data presents an anomaly or not based on the patterns it learned during training. The final step is final outcome is displayed through frontend. The prediction outcome is displayed to the user through the frontend of the web application. This provides users with insights into whether anomalies were detected in the input data, allowing them to take appropriate actions. Algorithms which are used in the project are GMM, which is Gaussian mixture model. It is a probabilistic model that assumes that the data is generated from a mixture of several Gaussian distributions. It models each cluster as a Gaussian distribution and estimates the parameters of each Gaussian. GMM is used in the project for anomaly detection because it can model complex data distributions and identify anomalies as data points that deviate significantly from the learned distributions. The next step is support vector data description. SPDD is one class classification algorithm inspired by support vector machines. It constructs a hypersphere in feature space with minimal volume around the target class, defined by a set of support vectors. The goal is to encapsulate normal data points within this hypersphere. SPDD is well suited for one class classification tasks where the focus is on identifying anomalies based on the compact representation of the normal data. By capturing the distribution of normal data within the hypersphere, SPDD can efficiently and effectively distinguish between normal and anomalous instances. The next model is one class support vector machine, which is OSVM. It is a variant of the traditional SVM algorithm designed for one class classification. It aims to find the hyperplane with maximum margin that separates the target class from origin in the feature space. Anomalies are the instances lying on the wrong side of this hyperplane. OSVM is utilized to classify instances as either normal or anomalous based on their position relative to their separating hyperplane. It is effective for identifying outliers or anomalies that deviate significantly from the normal data distribution. The next algorithm is Mahalanobis one class support vector machine, which is MOSVM. It extends OSVM by incorporating Mahalanobis distance as a distance metric instead of Euclidean distance. Mahalanobis distance considers the correlation between features by taking into account the covariance matrix of the data. MOSVM accounts for feature correlations in anomaly detection, making it suitable for datasets where features are interrelated by considering the covariance structure of the data. MOSVM provide more accurate anomaly detection results compared to OSVM. Coming to the next model, which is one class neural network. It is a neural network architecture designed for the one class classification task. It typically consists of single hidden layer within the linear or sigmoid activation functions and one output node. The loss function is equivalent to that of OSVM. One class neural network leverages the expressive power of neural networks for anomaly detection while incorporating the principles of one class classification. It learns to represent normal data patterns and identify anomalies based on the deviations from these learned patterns. The next algorithm is subclass dispersion one class support vector machine, which is SDO-SVM. It extends OSVM by introducing subclasses within the target class using the k-means clustering algorithm. It aims to capture the dispersion of normal data more effectively by considering subclasses within the target class. SDO-SVM enhances the discriminative power of the classifier by capturing the diversity of normal data distribution through the subclasses. This allows for a more nuanced representation of normal data, potentially leading to the improved anomaly detection performance. As an extension, we applied an ensemble method stacking classifier combining the prediction of multiple individual models to produce a more robust and accurate final prediction. Additionally, as an extension, we built the front-end using Flask framework for user testing with user authentication. We have used accuracy, precision, recall, and FN score, which are the performance metrics to evaluate all the classification models built in the project. So here we have performance comparison graphs for all the models built in the project. This is accuracy comparison graph, where x-axis represents all the algorithm names and y-axis represents accuracy score. Similarly, we will have for other graphs also. Coming to the accuracy, it is the proportion of correct predictions in a classification task, measuring the overall correctness of a model's predictions. This is precision score comparison graph. It is the ratio of true positive predictions to the total positive predictions, representing the model's ability to correctly identify relevant instances while minimizing false positives. This is recall comparison graph. Recall is also known as sensitivity or true positive rate. It is the ratio of true positives to the total actual positives, measuring a model's ability to capture all relevant instances without missing any. This is FN score comparison graph. FN score is the harmonic mean of precision and recall, offering a balanced measure that considers both false positives and false negatives, making it suitable for imbalanced datasets. The algorithm which performs well among all these metrics will be used for final prediction. So the extension algorithm stacking classifier is performing well among all the metrics, so it is used for final prediction. To execute the project, first we have to open the code folder which contains source code files. This is the code folder of the project. This is the static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap files. This is the templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content that to be rendered in HTML templates. This is the model file which contains the algorithm information and that will be loaded into the project code during runtime. This is the notebook.ipynb file. This is a Jupyter notebook file which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for the data science. This is the signup.db file. This file is a database file which is used to store the user information. Now we have to copy the path of the code folder from the address bar of the file explorer. So I'm copying the path. Now we have to open the Anaconda prompt. Using the cd command followed by the space, we need to paste the copied path and then click on enter. This will change current directory to the code folder's path. So here we can see that current directory is changed to the code folder's path. And here we need to type the command python space app.py and then click on enter. This will compile app.py file and it will execute Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, Flask framework will host the application locally at the default address. This is the local host and this is the port. Localhost and the port are the default address unless configured differently. Now we need to copy this local link provided by the framework and paste it in any web browser. So I'm copying the link. I prefer Google Chrome, so I'll paste it in that. Here we need to paste the link and then click on enter. This is web page of the project, which is displayed in the browser. And this web page is built by using the Flask framework. So here we can see a login link. First, we need to click on that. Here we need to give our credentials to sign in. Before signing in, if we are new users, we have to sign up. For that, we need to click on sign up button and enter all the registration details and click on register. I have already registered and I have an account in it, so I will directly sign in. For that, click on sign in and enter credentials. So I'm giving the username and the password and now click on login. I have logged in successfully and I'm redirected to prediction page where I need to enter all these parameters. Based on the given parameters, I will get the prediction. Before entering the parameters, we will understand them. So the first one is L4 SRC port. It is a source port number in the transport layer of the TCP or IP protocol stack. The next one is L4 DST port. It is the destination port number in the transport layer of the TCP or IP protocol stack. The next one is protocol. Protocol used for communication such as TCP, UDP or ICMP. Next one is TCP flags. Flags used in TCP packets indicating various control functions such as SYN, ACK, FIN and RST. The next one is client TCP flags. TCP flags set by the client in the communication. The next one is server TCP flags. It is the TCP flags set by the server in the communication. Coming to the next one, which is flow duration milliseconds. It is the duration of the flow of packets in milliseconds. The next one is duration in. It is the duration of the incoming traffic. The next one is duration out. It is the duration of the outgoing traffic. The next one is min TTL, which is the minimum time to live value observed in packets. Next one is max TTL, which is maximum time to live value observed in packets. Longest flow packet. It is the length of the longest packet observed in the flow. Min IP packet length. It is the minimum IP packet length observed in packets. The next one is max IP packet length, which is the maximum IP packet length observed in packets. The next one is DST to SRC average throughput. It is the average throughput from the destination to the source. The next one is TCP win max in. It is the maximum TCP window size observed in incoming traffic. The next one is TCP win max out. It is the maximum TCP window size observed in outgoing traffic. The next one is DNS query ID. It is the ID assigned to a DNS query. The next one is DNS TTL answer. It is time to live value in DNS packet response. We understood all the parameters, so we will enter them. I have entered all the parameters. Now we need to click on submit. So here I got the prediction as benign, which means there is no attack detected. Now we will enter other set of parameters. So click on home. I have entered all the parameters. Now click on submit. So here we got the prediction as scanning, which means attack is detected. Now we will enter other set of parameters. Click on back arrow. Click on home. I entered all the parameters. Now click on submit. Here we got the prediction as XSS. Now we will enter other set of parameters. Click on back arrow. And now click on home. I entered all the parameters. Now click on submit. Here I got the prediction as it is DDoS attack. Now we will enter other set of parameters and see what will be predicted. Click on home. I entered all the parameters. Now click on submit. So here attack is detected as password. Now we will try giving other set of parameters and see what will be predicted. Click on home. I entered all the parameters. Click on submit. Here we got the prediction as injection attack detected. Similarly, based on the given parameters, we will get off other type of attacks such as DOS, backdoor, MIT, and ransomware. Now click on sign out. Conclusion of the project. The project introduced a novel approach for anomaly detection in the Internet of Healthcare Things using deep learning based classifiers tailored to handle the unique challenges of the healthcare data. Through experimentation and evaluation, it was demonstrated that the proposed classifiers, including SDO-SVM, MOSVM, and one-class neural network, outperformed traditional methods like GMM and SPDD in terms of accuracy, precision, recall, and FN score. The stacking classifier extension showcased superior performance during testing, exhibiting improved accuracy and reliability in anomaly predictions compared to individual classifiers. Front-end testing confirmed its effectiveness by accurately processing user-inputted feature values, underscoring its suitability for real-world deployment. Moving forward, further research and development could explore the scalability and robustness of the proposed classifiers in large-scale healthcare environments. Additionally, efforts to enhance interpretability and transparency to the models could facilitate their adoption in clinical settings.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.